Hi everyone, and welcome to our chemistry special project, where we look at the reaction between baking soda and vinegar to demonstrate principles of chemical spontaneity. Before we get into the specifics of our experiment, let's first make an important distinction. There are two main types of reactions in our world, chemical and physical. Physical reactions, as the name implies, are simply changes in physical properties in an object, including its color and shape. Chemical reactions, on the other hand, are changes at the molecular level. Chemical reactions take place all around us every single day. From baking a cake to a rotting banana, chemical reactions surround us. Today, for our project, we will be focusing on chemical reactions. Here are the materials we used for this experiment: a bottle, vinegar, baking soda, a cork, and a paper towel.
We use these materials because vinegar, which is also known as acetic acid, and baking soda, which is also known as sodium bicarbonate, undergo a very interesting chemical reaction.
The reaction between baking soda and vinegar occurs in two steps. The first step is when the initial mixture of our two reactants produces carbonic acid and sodium acetate. The second step is the immediate decomposition of the carbonic acid initially produced into water and carbon dioxide gas. Thus, the overall chemical equation for this reaction is as follows. Vinegar, also known as acetic acid, reacts with baking soda, also known as sodium bicarbonate, to produce dissolved sodium acetate, water, and carbon dioxide. As we'll discuss later in this video, it is the production of the carbon dioxide gas that really drives the reaction. So, now that we've shown you the chemical formula, what do you think this reaction looks like in real life? Well, let's find out.
First, we poured about a cup of vinegar into a plastic bottle. Because we simply wanted to show this chemical reaction, we weren't particular with any of our measurements. Next, we placed baking soda into a paper towel and folded the paper towel around the baking soda. We then placed the paper towel filled with the baking soda into the bottle and placed a cork on top of the bottle. You can see what happened as the vinegar soaked through the paper towel. And again.
So, what did you notice in the video? It exploded. But why did this happen? To discover the reason behind the explosion, we'll have to dive deeper into chemical concepts of reactions.
So, what are we waiting for? Let's explore some chemistry.
The reaction between vinegar and baking soda is a spontaneous one, meaning that it will happen on its own without any need of external sources of energy to drive it forward. Spontaneity is represented by the symbol delta G. A negative delta G tells us that the reaction is spontaneous. And conversely, a positive one tells us that it's not. Delta G, or Gibbs free energy, is defined as the enthalpy of the system minus the product of the temperature times the entropy of the system. Delta G is a state function, meaning that its value does not depend on the path taken to reach it. The change in enthalpy, denoted as delta H, is the amount of heat released or absorbed by the system. If heat is released, delta H is negative, and if heat is absorbed, delta H is positive. Entropy, denoted as delta S, is a measure of the amount of disorder in a system. The universe always favors greater entropy. A positive entropy means the system is moving towards more disorder, while a negative one means it's moving away from disorder. In our experiment, the system moves towards more disorder, and so delta S is positive. In the reaction between baking soda and vinegar, heat is absorbed from the surroundings, and so delta H ends up being positive. Typically, spontaneous reactions are exothermic, meaning they release heat into surroundings, and delta H is negative. However, the reaction between baking soda and vinegar is an exception. Although this reaction has a positive delta H and is thus termed endothermic, it is still spontaneous, and we will see why in a minute.
We can make more sense of this if we look at the problem mathematically. Because there is subtraction in the formula for delta G, or Gibbs free energy, delta G will be negative in an endothermic reaction if and only if the value for T delta S, which is temperature times the entropy of the system, is positive and large enough to overcome the positive delta H. And that is exactly what happens in the reaction of acetic acid and sodium bicarbonate.
Although this reaction is endothermic, as it requires heat from the surroundings to form the final products, it is still spontaneous. This is because the value for T delta S is greater than the value for delta H. In other words, the entropy increase is sufficient enough to overpower the enthalpy change. Also, just a quick side note, the value for T is always positive as it is in kelvins.
Another important aspect of this reaction is that it is irreversible, meaning that once it begins, it continues to completion. In other words, it does not and cannot return to an equilibrium. A good example of irreversible reactions are combustion reactions. Although a reaction between acetic acid and sodium bicarbonate is not a combustion reaction, it is irreversible. This principle of being irreversible is important because it causes more and more carbon dioxide gas to be produced.
The accumulation of carbon dioxide gas in this experiment is what causes the cork to fly off of the bottle because the pressure of the gas builds up until the closed bottle can no longer contain it.
In summary, even though the reaction between acetic acid and sodium bicarbonate is endothermic, the entropy increase it causes is enough to make it a spontaneous reaction. And because it is spontaneous and irreversible, more and more carbon dioxide gas builds up in the bottle, causing the cork to be released. So, what can we learn from the reaction of vinegar and baking soda? Certainly a lot about Gibbs free energy and spontaneity. But also, we learned it is a great reaction to make a tomato fly through the air. Please enjoy!
Go.